Welcome to our ETSL lithium-ion battery research. My name is Devendra, and with me today are Nithin and Gaurav, my teammates. Moving on to the next slide for the introduction. Fast charging nowadays is becoming more and more important as lithium-ion battery capacities are increasing, so it takes longer to charge and discharge them, especially in electrical vehicles and other industrial applications. To increase the efficiency of this, we can increase the C rate, which is the charging rate, or we can change the cell temperature, and this can be done to fit the needs of the industry. However, the C rate and changing the temperature does affect the battery in multiple different ways. Having a lower temperature will result in lower chemical activity, and as a result, lithium plating on the electrodes can increase, which reduces the efficiency drastically. But on the other hand, if you make the temperature too high, this can result in self-discharge, which is not the safest thing to have. With this information, we're going to be testing the effective temperature on the lithium plating of the cell, and the way we're going to be doing this is by using internal or external heating. And now internal heating is done by using the AC pulses inside the cell to modulate the temperature. This is done by using the sine wave and changing the frequency and the current. And if you look on the left is the code that we use to model this, and the model that was used was the heat transfer equation. And using a current of 13.35 amps and to reach a temperature of 25 degrees Celsius, it took 8.3 seconds. Now I'll pass it off to Gaurav for the external heating.
So the external heating model is a model that we used based on the heat transfer equation that Devendra mentioned in the previous slide. I used that equation to build the MATLAB code, as you can see on the right over here. That runs through a for loop that calculates that solves the differential equation and calculates the time required for the cell to reach the target temperature of 25 degrees Celsius. As you can see on the left, there is the graph that shows the temperature of the battery versus the time, and the cell reaches its target temperature of 25 degrees Celsius in about 12.5 seconds with the lowest possible current of 6.671 amps. After building this model, we moved on to the 3D model, which was developed by other members of our team, and we had to process the experimental data gathered by them. This shows the 1C charging rate for the 3D model. The three graphs over here are representative of different variables versus the state of charge. The first graph shows us the voltage versus state of charge, and we can see that for the, batteries at initial temperature of 5 degrees Celsius do not reach the specified theoretical voltage of 4.2 volts, but they instead level off at about 4 volts. And in T naught values, T naught 25 degrees Celsius cells, which is the initial temperature 25 degrees Celsius, level off at about 3.8 volts. Similarly, the temperature that these cells are heated to in the second graph is can be seen as the T naught 5 degrees Celsius roughly tops out at about between a little under 20 degrees Celsius, and T naught 25 degrees Celsius is somewhere between 30 and 35 degrees Celsius. The lithium plating for the 1C charge rate for this cell can be seen as that the T naught 5 degrees Celsius cells have no lithium plating, as can be seen in the graph over here. It's a flat line. However, the T naught 25 degrees Celsius has some form of plating, which is roughly just under 100 moles per meter cubed. We next move on to the 3C charging rate, which, as we can see from the graphs, which are pretty similar to the previous slide. However, the graphs in this one top out at different state of charges. This is because with basic charging methods that we employ use a controlled voltage, which we aren't able to simulate for the model. So as you can see, for the cells at initial temperature of 5 degrees Celsius, they do reach the specified theoretical voltage of 4.2 volts, but they reach it at about 10% the state of charge. However, T naught 25 degrees Celsius reaches the specified voltage at about 70% state of charge. Similarly, for the lithium plating for this cell, we can see that T naught at 5 degrees Celsius has hardly any lithium plating, but T naught 25 degrees Celsius has some plating, about 40 to 45 moles per meter cubed. And the temperature curve similarly reflects different values. We can see that T naught 5 degrees Celsius heats up to a maximum temperature just under 10 degrees Celsius, and T naught 25 degrees Celsius heats up to a maximum temperature of 35 degrees Celsius. Moving on to Nithin.
In the first graph, we plot data for current and voltage versus time. We see that the time required to reach the cutoff voltage is roughly 1700 seconds, that is in constant current phase. One must observe that once the cutoff voltage limit is met, the battery enters a constant voltage phase. To maintain the constant voltage, the current through the cell falls. This phenomenon is due to the accumulation of lithium ions at the anode, which makes it difficult to apply charge across the terminals of the cell. No major difference is obtained in the 10th cycle of charging and discharging. In the decoupled anode and cathode voltage, We observe that the anode potential is still positive. This experimental result obtained stands in contrary to our theoretical simulation. Now moving to the next slide. In the 2C rate of charge, one must observe in the current and voltage versus time plot that the cutoff voltage is reached faster. Correspondingly, the current through the battery falls to a smaller value much quicker. In the decoupled voltage versus capacity graph, we observe that the anode potential remained positive. This is again contrary to our theoretical result. No major difference is obtained in the 10th cycle of charging and discharging. We would like to conclude that on charging with higher C rate and higher number of cycles, we do not see much of lithium plating as indicated by the positive anode potential. We can see from the results that as temperature increased, the voltage for given SOC decreased. On the contrast, the level of lithium plating did decrease for an increase in temperature, which is in line with what we expect. With the 3D model and MATLAB model, it is easy to see the relationship between all variables and the battery condition. Now passing it to Devendra for conclusion.
To conclude, all these findings are vital if one must try to work with lithium-ion cells in any capacity, ensuring that the conditions, ambient, otherwise, or under max load, are met so that the optimal working efficiency of the cell is achieved is imperative, and we end our presentation. Thank you for your time.